Okay, so we have last lecture we talk about DCT, and then we have talked about the long data analysis. Today we talk about the frequency analysis of a long signal using discrete Fourier transform. So, what we want to discuss is that if my signal is very long, how can I analysis using discrete Fourier transform? Let us say I have a signal whose length is infinite. Length is infinite. So, if I take entire signal, the length of the DFT will be huge. So, if I want to analyze frequency, analyze the signal, I have to take a small portion of the signal. Another problem, I have a signal which is not time invariant. I have a long signal, along the timeline signal change its property, non-stationary signal. Then if I take entire signal at a time for analyzing discrete Fourier transform, so what I will get? I get an average spectra. So, sometimes the signal is periodic, sometimes signal is noise, sometimes again periodic. So, if I take all together, I get a spectra, the periodic, noise and periodic, all average spectra. I do not want that one. I want to analyze the signal, small portion of the signal, and then again I want to synthesis that signal. So, that is called short term Fourier transform, that I will do after this lecture. I will explain that also. So, initially thought the signal is stationary, but the signal is very long. I have a long signal which is stationary. Let us say in case of a xn is a sequence, long sequence of a signal has to be analyzed, and let us say xn is nothing but a cos omega 0 n. So, I have a signal which is nothing but a x of n, which is cos omega 0 n. So, what I am saying? I am saying I have a signal x of n which is, let us say, cos omega 0 n. So, the frequency of the signal is omega 0, and that is cos omega 0 n has a long sequence. Let us L tends to infinity, long sequence. So, I cannot take whole sequence to analyze at a time discrete Fourier transform. So, let us say I select some L number of sample of this long signal and I do the discrete Fourier transform. So, I take let us say out of long signal I take L number of sample and then I do the discrete Fourier transform. So, if a long signal is represented by an xn, so DFT must be xk, but not. Why not? Because when I select some portion of the signal, what I am doing? I am saying the signal only, this signal non-zero, signal is xn is non-zero only the interval of 0 to L minus 1. Outside it, the signal is 0. So, that means basically I am multiplying 1 of x with x of n, multiplying 1 up to L minus 1. After that, I am multiplying x of n with 0. So, what we are doing? Basically, we are doing a signal multiplying an window function Wn. So, Wn is basically 1 if n varies from 0 to L minus 1, n varies from 0 to L minus 1, else it is 0. So, what I am defining? I have an x of n and I have an Wn which is 1, 0 to L minus 1, outside it is 0. So, when I take the DFT, basically I am not computing DFT of Xn alone, I am computing a DFT with Wn, and that DFT I am calculating. So, that DFT is not Xk, that is defined by which window. So, I am discretize the time also. So, here also time also has an index. So, that is called X of Nk. Now, what is X of Nk? So, if my signal is only cos, let us I take another slide here. So, when I say my signal is only cos omega x of n is equal to cos omega 0 n, then what is the frequency transform? What is the frequency representation of a cos function? If this scale is frequency, this is 0, then I said there will be a one component in here which is omega 0 plus, and one component will be here which is omega 0 minus. That is the frequency domain or Fourier transform of a cosine wave. If it is infinite, transform is infinite, that is the ideal case. But now what we are doing, basically I am multiplying x of n with a Wn. What is the Wn signal? Wn is nothing but a get function. So, what is the frequency response of the get function? Is nothing but a sinc function. So, when I take the DFT of that, then my x of nk is not x of k. So, it is not like this. So, what it will be? So, I can say my x of k, let us say I have n, I have said that n is 1, first window. So, I can say x of k, that is x cap k, it is not x k, x cap k is equal to half of w omega minus omega 0 plus w omega plus omega 0. That means this sinc function, so ideally what I will get? I will get, instead of an impulse at omega 0, I get a sinc function in here. This is my omega 0, and I get a sinc function in here also. So, what I am getting? I am getting a sinc function at the so I cannot say this is a particular omega 0 frequency. So, the power of omega 0 will be distributed nearby frequency also. So, I get a frequency band. So, what is the bandwidth? Now, what is the representation of the sinc function? You know that if the length of the window is L, then the sinc function is sine, told me 2 pi L by 2 divided by sine, so only not 2 pi, this is let us say omega. So, omega L by 2 divided by omega 2 into e to the power minus j omega L minus 1 divided by 2, omega L minus 1 divided by 2. So, that is the DFT of this one. So, what it is meaning? Meaning is that instead of getting a single impulse at omega 0, I get an bandwidth. So, this is the main lobe and those are called side lobe. So, this is nothing but a pi by, you can say pi by L. So, this is L by 2 and there will be a L by 2 minus L by 2. or I can say this is twice pi by L by pi by L, and this is pi by L in the discrete frequency range. So I can say, suppose this omega 0 is 1 kilohertz. So instead of getting an impulse at 1 kilohertz, if I take the DFT, I get an power distribution nearby 1 kilohertz. So not only single 1 kilohertz, but side by side frequency also impulse. So that is called DSP leakage. And it also affects the side lobe. So those components also get the power. So this is a power spectra. If I take the power spectra, so instead of getting in the power spectra, instead of getting an impulse on a particular frequency omega 0, I get an main lobe width and then this kind of things. Now make it little bit of complex. Let's go, instead of single frequency, I have a signal which has two frequency. One is omega 1, another is omega 2. So I have a sine wave, or let's say this is 500 hertz and this is 1.5 kilohertz. So two component, 500 hertz and 1.2 kilohertz. Again, if I take the DFT of a particular window, then I get this frequency response. So instead of, so if I say, if I ideal frequency response or spectrum of this signal is, there will be a peak at omega 1, there will be a peak at omega 2 this side, and there will be a peak at minus omega 1, and there will be a peak at minus omega 2. That should be the ideal response. But since I am multiplying by the window, so the window response will be convolved here. So that is the main lobe, and there will be a side lobe. Now see, if omega 1 minus omega 2 is less than 2 pi L, so you know the width of the main lobe is 2 pi by L. So sorry, pi by L, this is minus pi by L. So total width is nothing but the 2 pi by L. So I have a peak. So what is the ideal response? Ideal response is omega 1 and omega 2, minus omega 1 and minus omega 2. So what I will get? Instead of that, I will get this kind of response. So this is omega 1 and this is omega 2, and this width is nothing but a 2 pi by L. So you know that if I use a rectangular window which is a gate function, the sinc function has a main lobe at pi by minus pi by L to plus pi by L. So total width is 2 pi by L. Now see that if omega 2 minus omega 1 is less than 2 pi by L, so this separation, so this part is pi by L, this part is pi by L. So if it is less than pi by L, that means there will be overlap. So this is pi by L and this is also pi by L. So there will be overlap. So separation between the two frequency, if it is less than 2 pi by L, I cannot get a distinct frequency component omega 1 and omega 2 at the DFT analysis. So what I said, that then the two window function are overlap, and consequence two spectral line, I suppose to get one line here and one line here, are not distinguishable because they are in overlap. So what I required, when I analyze DFT, I want that there should not be an overlap. So omega 1 minus omega 2 must be greater than 2 pi by L. So, that is my resolution. So, if it is this, there will be no knot. So, two separate lobe in spectrum are distinguishable if omega 1 and omega difference between the two frequency is greater than 2 pi by L. So, suppose I have a component here, let us say 50 hertz component here, and let us say bandwidth in terms of hertz is let us say 30 hertz. So, I can say the resolution, frequency resolution which is defined by L is 30 hertz. Two frequency must be separate by 30. So, I can say twice pi L is my resolution, and that if I can only distinguish those frequency only, they are separable by 2 pi L. If there exists two frequency which is within 2 pi L, I cannot separate that. So, that is my frequency resolution. Is it clear? So, what is the limitation? Due to the multiplication of window in time domain signal, in frequency domain, I get a frequency response which is nothing but a combination of signal frequency response and the window frequency response. Now, see, if I want to increase the resolution, so if my side lobe width, if the side lobe width, the main lobe width is increases, then my resolution will be decreases. Broad spectra frequency resolution will be decreases. Okay or not? So, if I want to increase the frequency resolution, then this lobe should be very sharp. That is another problem. What is another problem? If I see, suppose I have a sinc function like this. If I plot the magnitude spectra, I will get like this. So, those is called side lobe and this is called main lobe. Now, if the side lobe is the noise, side lobe introduce noise for the other frequency. So, this is omega 0, this side lobe introduce noise for the other frequency. So, there is a true trade-off. I have to reduce this side lobe energy and I have to sharper the main lobe. So, I require a window whose main lobe is very sharp and side lobe is very less. That is my requirement for defining window. So, I require a window whose main lobe is very sharp, very narrow, and the side lobe error is very less. So, that is my window requirement. Now, if you see that window requirement, how do I define? So, that side lobe produce and leakage. So, if I want to reduce the leakage, there is different kinds of window are there. Hamming window, Hanning window, Blackman window, Kaiser window, which reduce the side lobe is obtained at the expenses of increase the width of the main lobe. Once the side lobe energy is reduced, but main lobe energy is increases. So, in a rectangular window, I may say the main lobe is sharp, but the leakage is very high. If I want to go to the Hamming window or Hanning window, maybe the main lobe is very wide and the side lobe leakage is very less. So, when I use Hanning window, the resolution of the frequency is reduced because of main lobe width is high. So, it depends which kind of analysis you want, which kind of analysis you want for your signal. That give you the trade-off of choosing the window function. So, Wn by default it is a rectangular window. But if I want to choose Hamming window, Blackman window, Kaiser window, then all window functions are there. So, it is then Blackman window is this function. So, I can generate Wn using this function. So, this is nothing but a Wn. Let us say I generate Wn up to 0 to L minus 1. I generate Hamming window 0 to L minus 1, which is Wn. I Hamming window Wn. So, this is the window function. Different window function I can use to generate Wn. So, at summary, when I want to analyze a signal in frequency domain, a long signal, I have to multiply the signal with a window. And the choice of the window depends on what I want. If I say, if I use rectangular window, the leakage is much more. So, if I say the rectangular window, my frequency, the spectrum may look like this. There is a noise, and then there will be a main lobe, there will be a noise, there will be a main lobe. So, this is my omega 1 and this is my omega 2. Now, if I use Hamming window, maybe this noise is reduced, but main lobe width may be increased. So, this is Hamming window. So, what I can do? It depends on my choice, that what kind of frequency analysis I want. So, there are a lot of window functions are available. You can use any one of the window. Okay? So, that is an important issue. Now, again, for a practical example, you can do it. Let us say I told you generate x of n with a frequency component of 500 hertz, 1.5 kilohertz and 2.5 kilohertz, and sample it Fs equal to 8 kilohertz. Then take a 200 sample and compute DFT and plot the spectrum of that DFT output. So, I want the plot, this axis is the k, this axis is the mod of xk cap. Then you can see. So, ideally what you expect? You expect there will be a spike, single spike at 500 hertz, 1.5 kilohertz and 2.5 kilohertz, depending on the amplitude you have multiplied. Now, when you say I am doing DFT of 200 sample, you can see it will look like this, due to the DFT leakage. This is the main lobe and there will be a noise. So, that overlap create a spectrum which is not clear peak. There may be a spectrum look like this, depending on the amplitude. So, I'll all of you can try it. Now, that this thing, this limitation is come into the picture of signal analysis. Real example is short term Fourier transform. In speech processing, we use short term Fourier transform for analyze the signal in frequency domain. You may say, sir, why we require a frequency domain? We are very happy with time domain. But suppose some modification you have to done in spectral level. So, you have to go to the frequency domain modification and then take the inverse DFT, you get back the signal. So, DFT analysis and IDFT is the synthesis. So, both are used in speech signal processing for short term Fourier transform, which I will explain in the next lecture. So, now you have an idea what will happen if my signal is long If I multiply by the signal, I take a small portion of the signal, that means multiplying by an window function. So, in the next lecture you can see how this is effect in synthesis and how this is effect in analysis both. Okay? Thank you.